Hello, my dear students. Today I will start with the remaining part of Unit 2, that is bending stresses and shear stresses in the beams. This bending stresses is also called as flexural stresses. And first we will discuss what is the theory of simple bending. Whenever a member is subjected to bending moment and shear force, the member undergoes certain deformations. And to resist that bending moment and shearing force, stresses will be developed in the section of the beam. All of you know now what is bending moment and shear force. So when bending moment and shear force developed in the beam, the stresses will be developed in the section of the beam in order to resist that. A beam is a structural member on which a system of external loads acts at right angles to its longitudinal axis. Bending moments and shear forces are set up along the length of the beam. Due to these loads, loads, hence the beam has to resist the action of the bending moment and shear forces. So the longitudinal stress produced at any section to resist the bending is known as the bending stress or flexure. Okay, what happens? The bending moments and shear forces are set up along the length of the beam due to the loads. So, beam has to resist the action of bending moment and shear force. To do that, the longitudinal stresses produced at any section to resist the bending is known as bending stress or flexure. Now, we will, and also the bending is usually associated with the shear. However, for simplicity, we neglect effect of shear and consider moment alone. And also we know that this is true when the maximum bending moment is considered, shear force is zero. That all of us know. In the last chapter I have discussed about that. So the only the bending moment is considered to find the stresses. Okay, see here, such a theory wherein stresses due to bending alone is considered is known as pure bending or simple bending theory. Okay, here only the effect of bending is considered. Okay, or it can also be defined as if a beam is bent with the application of a constant bending moment without being subjected to shear, then it is said to be in a state of pure bending or simple bending. Okay, so in the simple bending, what happens? There is only the bending moment. Okay, the beam is not subjected to shear. So such a type of bending is called as pure bending or simple bending. We can see this example, a simply supported beam. Okay, here this is RA and this is RB, simply supported beam AB, and it is subjected to 2-point loads P and T, which is at a distance of A from the left support and B from the right support. Okay, all of you know now how to calculate the reaction, so have not shown the calculation. So when you consider sigma V equal to 0 or vertical forces equal to 0, what is that? RA plus RB is equal to P plus P, that is equal to 2P, and take moment about A, so that is MA, summation of MA is equal to 0, so you get you have to write the equation, that is minus RB into L plus P into L minus A plus P into L minus A. Okay, so when you simplify this, you get RA and RB is equal to P. Okay, that is the first step. After that, you have to draw the shear force diagram. This is shear force diagram. So when the shear force diagram is drawn, how you can draw shear force at B, that is right side upward, is negative. So minus, okay, minus P you get. So and at P also, here it is same between this, and at this point it is 0, minus P plus P, that is becomes 0. So here there is no loading, and again here it is plus P. Okay, so this is plus P, this is minus P. Then draw the bending moment diagram. So at B it is 0, and at A also it is 0, and here it is P into A, and here also P into A. So in between there is nothing. So this portion, that is called as pure bending. Okay, this is a very good example for pure bending. Next we'll see what are the assumptions in the theory of simple bending. The following are the assumptions made in the theory of simple bending. The first one is the material of the beam is perfectly homogeneous. This is the common assumption in all the theories. That is, homogeneous means the same kind throughout, and isotropic, that is equal elastic properties in all the direction. And second assumption is the beam material is stressed within its elastic limit, and thus it obeys Hooke's law. Hooke's law states that stress is directly proportional to strain within the elastic limit. So the beam material is stressed within elastic limit, and it thus obeys the Hooke's law. Then the transverse sections which were plane before bending remains plane after bending also. This is the third assumption. Next assumption is each layer of the beam is free to expand or contract independently of the layer above or below it. So the beam is allowed to expand and contract freely above and below the layer. Okay, and the value of E, that is Young's modulus of elasticity or modulus of elasticity, is the same in the tension and compression, and the beam is in equilibrium, that is there is no resultant pull or push in the beam section. So these are the some of the assumptions made in the theory of simple bending. Now we will see what is this theory of simple bending. Consider a small length of a simply supported beam subjected to a bending moment as shown in the figure A. Let us consider this beam RS, and it is subjected to the bending moment here. This is M. Okay, both the sides. Now let us consider the two sections AB and CD, which are normal to the axis of the beam RS. Due to the action of the bending moment, the beam as a whole will bend as shown in the figure. You can imagine when you apply the bending moment here in this direction, what happens? The beam bends. So the beam bends like this. Okay. Since we are considering a small length of dx of the beam, let us consider the small length dx. Therefore, the curvature of the beam in this length is taken to be circular. Okay, so the curvature of the beam is considered as circular. Okay, now we have considered only this small length dx. So what happens here? It can be observed that all the layers of the beam which were originally of the same length do not remain of the same length anymore. Can see here all the lengths have changed, here also, here also, here also, all the layers, and the top layer of the beam has suffered compression and reduced to A dash C dash. You can see here this is compressed because of this load. This is compressed. It is reduced to A dash C dash, and here this bottom layer is elongated and it is increased to B dash D dash. Okay, so now as we proceed towards the lower layers of the beam, we can find that the layers have no doubt suffered compression, but to lesser degree. And means on the top layer there will be more compression. As we go on proceed towards the lower layers of the beam, we can find that layers have suffered lesser degree of compression until we will come across the layer RS, which has suffered no change in its length through bend into R dash S dash. Here there is no change in the length. Okay, this remains same length, but this is shortened and this is elongated, but there is no change in the length of R dash S dash. And here, if we further proceed towards the lower layers, we find the layers have suffered tension, as a result of which the layers are stretched. So, I have told that it is increased in the length. If you proceed towards the lower side, what happens? There will be increase in the length. So, it is stretched. So, the layer BD is changed to B dash D dash. So, it is stretched. Okay. So, here, what happened? The amount of extension increases as we proceed lower until we come across the lowermost layer BD, which has been stretched to B dash D dash. Now we can see that the layers above have been compressed and those below RS have been stretched. Okay, the topmost layer is compressed and the bottommost layer is stretched, means there will be a tension. The amount by which layer is compressed or stretched depends upon the position of the layer with reference to the RS. Okay, this layer RS, which is neither compressed nor stretched, is known as neutral plane or neutral layer. Okay, so the middle layer, it is neither compressed nor stretched, it remains same, so that layer is called as neutral layer or neutral plane. This theory of bending is called theory of simple bending. I hope all of you understood. Means when you apply the bending moment on the simply supported beam, what happens? The top layer is compressed and the bottom layer is stretched. So there will be a compression in the top layer and tension in the bottom layer, but the middle layer, that is the layer which is neither compressed nor stretched, is called as neutral plane or neutral layer. So this theory of simple bending is called as theory of simple bending. Now we'll see what is sagging moment and hogging moment. I've already explained in the shear force and bending moment calculation. Here you can see that when you apply the moment here on both the sides, the beam bends like this. So here this is the top layer, it is compressed, and this is the bottom layer, this is stretched. Okay, so that's why the arrow mark is shown like this. Here it is compressed. So the neutral axis, this is a rectangular section of the beam, and here the stresses are developed in this direction. So the top one is subjected to sigma C, that is compression, and the bottom layer is subjected to the tension. So stresses developed are tensile stresses, so that is sigma T, and this is sigma C, that is compression stresses. Similarly, we will see the hogging moment, that is negative bending moment, when you apply the load in this direction. Okay, on before that was sagging, so upward direction. Now it is in this direction, downward direction. What happens? The top layer is stretched and the bottom layer is compressed. Here you can see this. Okay, so neutral axis, so position of the neutral axis remains same. So there will be tension on the top and compression on the bottom. So stresses developed here on the top layer is tensile stresses and the bottom layer is compression stresses. I hope all of you understood. In the case of sagging moment, the diagram is like this. Compression is on top and tension on bottom. But in the case of hogging moment, there will be tensile stress in the top and compression stress developed in the bottom of the fiber. Okay, so this is about sagging and hogging bending moment, and also I'll explain once again. The fibers below the neutral axis get stretched, so fibers are under tension. Fibers above the neutral axis get compressed, the fibers are in compression. Hogging, fibers above the neutral axis get stretched, so fibers are under tension, and here the fibers below the neutral axis get compressed, so fibers are in compression. In between there is a fiber or layer which neither undergoes tension nor compression. This layer is called neutral layer, where the stresses are zero. The trace of this layer on the cross section is called the neutral axis. And also we'll see what is the relationship between bending stress and radius of curvature. So this is the formula, that is sigma b divided by y is equal to E divided by R, or sigma b is equal to E into y divided by R. Since E and R are constants in this expression, therefore the stress at any point is directly proportional to y, that is the distance of the point from the neutral axis. Since the bending stress is inversely proportional to the radius, therefore the maximum stress, the radius should be minimum, and vice versa. So this formula is very important. You should remember while solving the examples. Let us continue with the other topics in the next class. Thank you.